You're surrounded by this invisible storm of electrical noise, like right now. So how is it that what you're hearing from me is crystal clear? Well, the answer is inside a tiny but absolutely brilliant circuit, the differential amplifier. I mean, have you ever really wondered about that? You're on a call, you're listening to something, and even though you're literally surrounded by electrical wiring, all you hear is a clean signal. How in the world does your device know what to listen to and what to just completely ignore? That's the exact problem we're going to solve today. Because here's the reality. The signals our devices are trying to capture, everything from your voice to a heart rate sensor, they're incredibly weak, just tiny little whispers. And all around them is the sea of electrical noise from power lines, motors, you name it. Without a way to separate the signal from the noise, our technology would be a total mess. So, how do we tackle this noisy problem? Well, here's our game plan. We're going to start in this world of noisy signals. Then I'll introduce you to the amplifier's secret weapon. We'll see exactly how it rejects all that noise, peek behind the curtain at how they're designed for peak performance, and finally we'll go on a hunt to see where these things are hiding in your world. So what is this secret weapon that can basically hear a whisper in the middle of an electrical hurricane? It's called the differential amplifier. The absolute genius of this circuit comes down to just two words: difference and common. It's designed from the ground up to look at two different inputs and only care about what's different between them. Anything that's the same on both, it just throws it away. And this simple formula perfectly illustrates that core idea. The output voltage, Vout, is just the differential gain, we call it AD, multiplied by the simple subtraction of the two inputs. It's so elegant, right? Find the difference, then make it a whole lot bigger. Okay, so how does this clever trick of only focusing on the difference actually work in practice? Well, it all comes down to two totally distinct modes of operation. This is where the noise-canceling magic really happens. This right here is the key, okay? Imagine two people pushing a swing. If they push in opposite directions at the exact same time, that swing really moves, right? That's our real signal in differential mode. It creates a big difference the amplifier can grab onto and boost. But what if they both push in the same direction? Well, they just kind of cancel each other out. The swing barely moves. That's common mode. Noise like that hum from a power line hits both input wires at the same time, in the same way. The amplifier sees the same thing on both inputs, subtracts them, gets zero, and just rejects it. And this is that exact scenario. That 60 Hz hum from your wall outlet is literally everywhere. A good differential amplifier just sees that hum on both of its inputs, subtracts one from the other, and poof, the noise is gone. It just cancels itself out, while the signal you actually care about gets a free pass. So, how do we actually measure how good an amplifier is at this amazing noise-canceling trick? That's where this metric called the Common Mode Rejection Ratio, or CMRR, comes into play. You can think of it as its official report card for getting rid of noise. And the crucial takeaway here is you want a high CMRR, a really high one. So what does that actually mean? Well, let's say an amplifier has a CMRR of 100 decibels. That means the signal you want is being amplified 100,000 times more than the noise. That is the difference between a garbled, unusable mess and a perfectly clear signal. But achieving that incredible level of noise rejection doesn't just happen by accident. Oh no, it takes some very careful, very precise engineering. There are really three essential things that designers have to get exactly right. Okay, first up is input biasing. This basically sets the amplifier's ready state, kind of like a sprinter in the starting blocks. Second is transistor matching. This is all about making sure both sides of the amp are perfectly balanced, like a great stereo system. And third, the load configuration. That determines the amplifier's power, how much it can actually boost the signal. This is such a great way to think about it. For that noise cancellation to work perfectly, the two input transistors have to be like identical twins. If one is even a tiny bit different from the other, the whole balance gets thrown off and noise starts to leak through. It's all about perfect symmetry. And here's another fantastic analogy, this time for the load configuration. So instead of using plain old resistors, which are kind of like a basic engine, designers can use what are called active loads. These are much smarter circuits that give you a huge boost in amplification, that's the gain, without wasting a bunch of power. It's all about working smarter, not harder. Okay, so we've seen how they work, we've seen how they're designed, but where are they? Well, the short answer is they're everywhere. Let's connect all this back to the stuff you use every single day. I mean, just look at this. In your smart home devices, they're amplifying tiny signals from sensors. In an ECG machine in a hospital, they're picking up faint heartbeats while totally ignoring electrical noise from the body. They are the reason your USB devices can send data back and forth so reliably, and they're why modern robots can move with such incredible precision. They are the gatekeepers of clean data in our digital world. And here it is, the kicker. If you've ever heard of an op-amp, which is one of the most fundamental building blocks in all of electronics, then you've already met a differential amplifier. It's the core, it's the engine, it's the very first stage of almost every single op-amp out there. It's truly foundational. So let's do a super quick recap of what we've covered. The main thing to remember is that differential amps amplify the difference and reject what's common. That's their noise-killing superpower. Their performance all comes down to careful design of biasing, matching, and loads. You always want a high CMRR for a clean signal, and these circuits are the fundamental starting point for op-amps and just thousands of devices we all rely on. And that brings us to a final thought. We've just pulled back the curtain on how electronic noise gets filtered out of our lives. It kind of makes you wonder, what other kinds of noise, whether it's informational or social, are we filtering out, or maybe failing to filter out every single day? It's a pretty fascinating question. Thanks for joining me on this deep dive.